Alright, so now that we know what equilibrium is, we're going to look a little bit deeper at some of the math that we can do behind it, and what we can do with this equilibrium, and that is going to bring us to the equilibrium constant. So we have the rate constant and the equilibrium constant. Both of them are K. The equilibrium constant is capital K, not lowercase k like rate. So again, lots of similarities. Make sure that you're putting in your head which is which and keeping them separate from each other. You learn them really close together, so it's easy to get them mixed up. All right. How you can calculate the equilibrium constant is you've seen you have A plus B will give you, and this is a way of doing equilibrium where you have one arrow and the other arrow, you just take out the middle part, okay, gives me C, the products C and D. Well, we also have to be worried about their coefficients. So the people who came up with this gave these coefficients, J, K, L, and M. Okay, equilibrium constant, what is your capital K, and it is your products, so these guys, so the concentration of my products raised to the power of their coefficients. Over sorry, I'm trying to change colors here. The concentration of my reactants raised to their coefficients. Okay, so it is always products. Get used to saying this in your head, over reactants, because we will see this a lot. Products, reactants, products over reactants, always, always, always. Okay, you can calculate that out. You have to have these numbers given to you. Either their concentrations or their numbers are determined experimentally, and so you don't just pluck them out of thin air. Somebody has to give these products to these numbers to you, but you put in your concentration of your reactants, however many reactants you have, raised to their powers, divide it by the concentrations of the am I saying that right? Concentration of your products raised to their coefficients over the concentration of your reactants raised to theirs. Work through that problem, the problem that is on page 583. They've got all the answers there for you, and work through. That will help you with this next part, because they're bringing up some rules that kind of help you cheat a little bit, but without seeing that, without working through that, it'll be harder to do this. So once you've got that set up, if I'm looking at my equilibrium, and I'm looking at it this way first, so then I would put my products over my reactants. And then I want to look at it this way. I can just flip it so that instead of going concentration of C, L, concentration of D, M, concentration of A, J, concentration of B, K. Instead of having to go through and plug everything in with these numbers flips, I already found K, and it just becomes 1 over K. Okay, and similarly, if I multiply it by everything by 6, then I can just multiply that or raise it to the 6th, and you get the same answer. Is all that they're saying there. K has no units, so we should not worry about units with K. All right, the last thing that we need to worry about. When we were talking about it before, we had two graphs. We said we had the concentration versus time, and they very, very rarely meet and become one line, right? It's usually here and here, something like that. You have your reaction rate versus time. That is what is going to merge. Okay, so similarly, my concentrations, my K will be constant no matter what my concentrations are. That's part of the cool thing about this. If I start with 600 gallons of nitrogen and 10 gallons of hydrogen, the equilibrium constant will be the same as if I start with 60 gallons of nitrogen and 60 gallons of hydrogen. Okay? The constant doesn't change. The concentrations do. They are not constant, okay? So K, if you solve for K, then you can go in and put it back in and say, okay, so I have my K now. If I have this much instead of this much, how much of this will I get back out? That's where it becomes very powerful, is because you can start predicting what the concentrations will be at a given temperature after having only done it once, instead of having to do it a billion different times. And that is shown on page 586.